Welcome to the Ready Academy. Tools for teaching, tools for learning, tools for life. In this video book, we cover simple machines. This content was produced with AI assistance and reviewed by a human instructor. We'll continue with work, mechanical advantage, and efficiency. Work as the master bookkeeper. A ramp does not reduce the work needed to move a load. It spreads that work over a longer path, so the required force at any moment is smaller. Every analysis ahead rests on the equation that makes this precise. Equation 2.1. Work, W, equals force, F, times distance, D. Work is measured in joules. 1 joule equals 1 newton, times 1 meter. A machine receives input work from your effort and delivers output work to the load or resistance. For an ideal machine with no friction, these two quantities are equal. Throughout this series, we will use input and effort interchangeably. Similarly, you will see output, load, and resistance used interchangeably, as they hold the same meaning in the context of simple machines. Equation 2.2. Effort force times effort distance equals resistance force times resistance distance. For a frictionless machine, work in equals work out. This is the conservation of energy applied to machines. From this single equation, every ideal mechanical advantage formula in this video book is derived. Rearranging equation 2.2 reveals the trade at the heart of every simple machine. Equation 2.3. The ratio of output force to input force equals the inverse ratio of the distances. Multiply force by a factor of 5, and your hand must travel 5 times as far as the load. You gain force only by giving up distance. This trade, force for distance or distance for force, is the single idea behind every machine in this video book. Animation 2.1. Two paths raise the same crate to the same height. The steep short ramp demands a large force over a small distance. The gentle long ramp demands a small force over a large distance. A shared work counter ticks identically on both sides throughout. Force times distance is unchanged regardless of the path taken. Mechanical advantage, ideal versus actual. The ideal mechanical advantage is the force multiplication of a perfectly frictionless machine, calculated from geometry alone. The ratio of effort distance to resistance distance, measured with a ruler rather than a force gauge. Equation 2.4. Ideal mechanical advantage equals effort distance divided by resistance distance. It tells you the best force multiplication this machine's geometry can ever provide. The actual mechanical advantage is the force ratio you measure, real forces acting on a real machine, where friction and other losses eat into the output. Equation 2.5. Actual mechanical advantage equals the output force divided by the input force. For any real machine, friction converts some input work to heat, so AMA is always strictly less than IMA. Efficiency is the fraction of input work that emerges as useful output, the number that captures how much friction removes. Equation 2.6. Efficiency, eta, equals output work divided by input work, which also equals AMA divided by IMA. No real machine reaches 100% efficiency. Friction always takes a cut. Rearranging gives the most useful design formula. Actual mechanical advantage equals efficiency times ideal mechanical advantage. Equation 2.7. AMA equals eta times IMA. A machine with 85% efficiency and an ideal mechanical advantage of 10 delivers only 8.5 times your input force in practice. A well-lubricated lever or quality block and tackle reaches 90 to 95% efficiency. Screw jacks are far worse. Even well-lubricated screw jacks have efficiencies of only 15 to 20%. The rest of the input work lost to friction along the threads. Ramp efficiency. A worker uses a 4-meter ramp to slide a 500 Newton crate up to a loading dock 1.2 meters high. She measures that she must push with 180 newtons parallel to the ramp. Find A, the IMA, B. The AMA, C. The efficiency, and D. Verify using the definition of work directly. Step 1. IMA from geometry. Divide the slope length by the vertical rise. IMA equals slope length divided by height, 4 divided by 1.2, approximately 3.33. An IMA of 3.33 means for every meter the crate rises, the worker's hands travel 3.33 meters along the ramp. This is the geometric promise of the incline. Step 2. AMA from measured forces. Divide the output force by the input force. AMA equals 500 divided by 180, approximately 2.78. AMA is less than IMA. Friction is reducing the actual force multiplication below the geometric ideal. Step 3. Efficiency. Divide AMA by IMA. Efficiency equals 2.78 divided by 3.33, approximately 0.83 or 83%. Step 4. Work check. Compute output and input work directly from force times distance. Output work equals 500 newtons times 1.2 meters equals 600 joules. Input work equals 180 newtons times 4 meters equals 720 joules. Efficiency from work. 600 divided by 720 equals 0.83, confirming the same answer by an independent route. The ramp is 83% efficient. Friction consumed 120 joules of the 720 joules of input work as heat. Pulley system. A 1,200 Newton steel cabinet is lifted 0.8 meters by a pulley system. The user pulls 3.2 meters of rope with a force of 420 newtons. Calculate A, the IMA, B, the AMA, and C, the efficiency. Pause the video now and give it a try. From efficiency to work loss. A simple machine has an IMA of 5. Tests show that to lift a 250 Newton load, the user must apply 65 newtons. Find A, the AMA, B, the efficiency, and C, if the load is raised 0.4 meters, how much input work is required and how much energy is lost to friction. Pause the video now and give it a try. A salesman claims his hand crank ratchet hoist has a mechanical advantage of 50 and 100% efficiency. Why should you be skeptical of either number, and which one is closer to a violation of physics? That wraps up work, mechanical advantage, and efficiency. Next up, Section 3, the lever. If you found this helpful, like and subscribe, and support the channel.